Now that we learned a little bit about absolute maxes and mins, let's go back to local maxes and mins. Now I'm going to start from another seemingly different place, but I'm going to connect the concepts, don't worry. I'll still use purple for this. A critical value of a function is a value in the domain such that f prime of that value c equals 0 or does not exist. A critical point is the critical value paired with its y value. So if I just draw another big graph, and again, we're just visualizing this stuff right here. And maybe we consider this guy and then this guy. Something similar to what we had before in that last video. Or no, rather we should do it the other way, right? Do a hole. Do a dot. Do that. And maybe something like that. Actually, let's make this maybe a little more interesting and do one of these guys. There we go. Let's do that, right? And we have some points of interest. I'll call these A, B, C, D, E, G, H. That's a G, not a J. G, not a J. Okay. So a critical point, remember, is a point where the derivative is 0 or does not exist. So let's just go ahead and get two little things going on here. F prime, I'll just say f prime equals 0 or f prime does not exist. Okay. And I'll just say, okay, well, let's just take a look, right? F prime equals 0 at A. Maybe I'll use the at symbol at A. B, right? F prime equals 0. We have a horizontal tangent line. Same here. F prime equals 0, which we know because we have a horizontal tangent line, right? The slope of the tangent line is 0. Now contrast that with point C, where the derivative does not exist, the function doesn't exist. And we have a similar issue at D. F prime of D, f of D exists, but f prime of D does not exist. F prime of E does not exist. F prime of G does exist. F prime of H does not exist, right? So it's a corner. Okay. Now, Fermat has a theorem that says if f has a local maximum at C and f prime of C exists, then f prime of C equals 0. And sure enough, if we go ahead and look at this example, the times that f prime does exist, and we do have a local min, f prime of C equals 0. So this tracks. So let me just go ahead. Let's shrink this guy down. Stick it right there. All right. And anyway, there's a proof of this in another textbook. If you're interested, I'll print it out for you. Okay. So let's just look at a couple of examples, right? Here, we have a set of axes. We have a graph. Maybe we have something like this. We have C. I'll call this maybe C1, C2. And here, right, we have a local maximum. F prime of C1 equals 0. Here we have a local minimum. f prime of C2 equals 0, right? So there we go. Local max, local min. Let me actually point that out. How can we have a local max or min, but the derivative does not exist? Well, just use your imagination. You could have something like this. Something very bizarre like this. Right? And here, we definitely have local maxes and mins, but we also definitely have things that are not differentiable. Right? And f prime of C1, f prime of C2 do not exist. All right? And is it possible to have a derivative that's equal to 0, but there's no local max there? Well, yeah. Again, let's use our creativity a little bit. And we could think of a function like this. Let me just make that a little clearer right here. Where right here at C, we do have a horizontal tangent line. Let me try to move that line a little bit better. Maybe right there or so. There's a horizontal tangent line right there at that one exact point. But f prime of C equals 0, but f of C is not a local max or min, right? It's not bigger than all the values in any interval or any neighborhood, and it's not less than all the values in any neighborhood. So we say that the point C, f of C, is a saddle point. Term I might use every now and then. That's what it means. So let's put this all together. Suppose that we have a function that's continuous on a closed interval. We know by the intermediate value theorem that f must have an absolute max and an absolute min. By Fermat's theorem, we know that if f has a local max or min, then either f prime of C equals 0 or f prime of C does not exist. So this is a technique for finding absolute maxes and mins within an interval. Okay? We're going to use local maxes and mins along with some endpoints to find absolute maxes and mins. So first off, what we want to do is we want to find all critical numbers of f in the interval a to b. Then we plug in a and b into f, and you choose the highest and lowest y values in 1 and 2. And whatever you get, that's the absolute max and min. So for example, consider this function. In the interval -3 to 5, what are the absolute max and min values? So step 1, we're going to take the derivative, f prime of x, and we're going to set it equal to 0. Now this is not so bad, right? X squared minus 12x. And we're going to set it equal to 0, okay? And then this implies that we can factor out, if you notice, we can factor out an x squared, or sorry, a 3x. X minus 4 equals 0. And so this implies x equals 0 and x equals 4. And we check and see, yes, both of those are in our interval from -3 to 5. And while we're at it, let's just note that f of 0, right, f of 0, f of 0 is going to equal what? It's going to equal 5. 0 cubed minus 6 times 0 squared plus 5 equals 5. F of 4, it's a little gross. 4 cubed minus 6 times 4 squared plus 5 equals, this is 64 minus 96 plus 5. I think I'm getting negative 27. Okay. 2, we're going to plug in f of negative 3. Lovely. That's going to give us negative 27 minus 54 plus 5. That equals negative 76. F of 5 equals, what is that going to equal? 125 minus 150 plus 5, and that's going to equal negative 20. So for part 3, we just look at all these values, right? We have f of our critical numbers. We have f of our endpoints. Right, so that's step 2. And we just find the highest and lowest of these values. So we just say f of 0 equals 5 is the absolute max. And f of negative 3 is the absolute min on the interval from negative 3 to 5. That's all we've got. That's how you find the absolute max and min of a function on an interval.